Dima Arinkin from University of Wisconsin-Madison, who will speak about singular support of categories. So Dima, go ahead.
All right. Well, thank you very much for the invitation. I don't know if I'm still supposed to say that it's a pleasure to be here if I'm only here virtually, but well, it's definitely a pleasure. So let me share the screen. And please let me know. So I'm telling you what I'm doing so that you can tell me if it doesn't work as expected. Yeah. So there should be something, and now there should be something meaningful.
Yep. Yeah, it's
okay,
visible.
Good. So yeah, so I'm going to talk about the singular support of categories, and so the plan. Well, the plan is written down, but let me actually talk about it a little bit. First, I'll discuss some motivation. I know that in my announcement I said motivation will, well, relation to the geometric Langlands will come at the end, but let's discuss it in the beginning so that I don't run out of time. So then it's as a bit of a review, as a way to get into this singular support of categories, I want to talk about descent in the categorical setting, which might be one categorical level higher than, well, than descent normally appears. And then from this, this idea of singular support it basically just jumps at you. It's born naturally, and it's born out of the distinction between things that have finite Tor dimension, things that are perfect, and things that are not perfect. So this support, as it often happens, is about imperfections. I would really like to say at least something about an example. So we'll see. I think it makes things more meaningful. And then I'll finally formulate what the precise statements. All right, so let's look at motivation first. Well, the point is that whenever there is some kind of geometric object, I don't know what that's supposed to be, so a geometric object on some space, it's really important, maybe one of its most fundamental characteristics would be its support, which basically tells you where the object is zero, rather where it's not zero, and then the complement is where it's zero. So, but often you can say a little bit more, and this leads to these ideas like that sometimes called some kind of version of singular support, micro support, or so on. So often you can say not just whether it's zero, whether it's non-zero at a particular point, but you might be able to say that it's non-zero in particular directions at this point. Whether it's directions or co-directions, it's subtle question. Anyway, so maybe the most classical example comes from theory of distributions, just a more generalized version of functions, where you can talk about singular support, a wavefront. Then maybe a more familiar example in algebraic geometry is the singular support of D modules. I guess I could also add perverse sheaves here, constructible sheaves, let's say perverse sheaves, where you can associate to a D modulo to a perverse sheaf its characteristic variety. It's a subvariety of the cotangent bundle, and basically it measures in which direction the object fails to be a local system.
If you micro-localize, then it reduces to the usual support. Yeah.
Well, I mean, that's from my point of view, this is the way to calculate it. So so for example, yes, for example, for distributions, right? If you want to think about support, if you can do something like maybe you can apply the Fourier transform, and then you can, then this mysterious support becomes more geometric. Is this a reasonable answer?
Yeah, absolutely.
Yeah, all right. So then another situation where a similar framework appears is when you look at coherent sheaves on local complete intersection, in which case you can have, there is a singular notion of singular support, which basically measures exactly the imperfection of a coherent sheaf, in which direction it fails to be perfect. And the goal of this talk is to explain what happens when you deal with, construct a framework when one deals with categories. So one can say that this list of examples lives on 3 levels of categorical hierarchy. Like we begin by looking at essentially at elements, at vectors, I guess, in a vector space. Then the next step is looking at objects in some categories. And now we want to go all the way to categories, or if you like, to objects in the 2 category, in some 2 category. All right, this is all, I mean, this looks interesting, at least to me, but there are more practical reasons to look at this. At least, well, practical from the point of view of the geometric Langlands program. So I don't want to go very deeply into this, especially because this whole discussion only happens on the one side of geometric Langlands program. But roughly speaking, the situation is as follows. So the original first formulation, the first version of the geometric Langlands program that was formulated was a global version where naively the goal is to understand, the first approximation, the goal is to understand coherent sheaves on the space stack of local systems on a Riemann surface or on an algebraic curve. And then it turns out that this naive formulation doesn't work, that it has to be corrected. And this correction has a name of, it's called Arthur parameters in the classical geometric, in the classical Langlands program. And so, and the way to introduce Arthur parameters, so the goal is to take this and put it into the geometric setup. And in the global geometric setup, this is done by using the notion of singular support for coherent sheaves. So in other words, this goes back to this line in the list of examples. So, and this was done in a joint work, in my joint project with Dennis Gates-Goring. So, however, besides the global geometric Langlands program, there is also its local version. And one reason why, in some ways it's simpler, but in some ways it's more complicated. And the way it's more complicated is that you often have to work at one step higher on this categorical, on this hierarchy of categorification. So from the naive point of view, the local geometric Langlands program is about understanding categories over some space of local systems, more precisely the stack of local systems over a punctured disk. And so, yeah, so the emphasis here is that what used to be coherent sheaves now should become categories. And again, from, so to say, from classical intuition, we know that this naive answer needs to be corrected, that Arthur parameters also have to appear in the local geometric Langlands program. And to do this, one has to introduce the notion of prescribed the notion of singular support for categories. And this is my goal today. So let me also say that there is a very interesting connection between this and somehow maybe the more concrete, between what I'm going to talk about now and the more physical and in some ways more concrete constructions by Kapustin, Rozansky, and Saulina. So I'm not going to say I'm not going to say anything more, but if you know something about their research, you will see similarities.
Dima, can I ask a quick question?
Of
so
course.
In the global picture here, the local systems should place the role of the underlying variety, and
Yes.
the signal support should be sitting inside of some kind of a tangent bundle.
Absolutely.
Okay.
Yeah. So it's the same. So the difference is that in the global setup, you consider local systems on a curve, and this forms something that looks like a local complete intersection. And for coherent sheaves on a local complete intersection, the singular support sits in a shifted cotangent bundle. While in the local setting, everything kind of shifts in various directions. So instead of having a compact curve, we have a punctured disk. And local systems over a punctured disk now form a smooth, well, it's not quite Artin stack, but to the extent to which it's an Artin stack, it is smooth. So there is no room for local complete intersectedness, so to say. There is no, the shifted cotangent bundle is trivial. However, it turns out that for categories, what's important is the actual cotangent bundle, not the shifted cotangent bundle. So the analogy is for local complete intersection, the important object is the shifted cotangent bundle. For categories over a smooth guy, what's important is the actual cotangent bundle. So in this way, it's like this theory is a bit of a mix between, it's an upgrade of theory of coherent sheaves, but of singular support for coherent sheaves, but in some ways it's also similar to D modules and perverse sheaves because it's interesting even on a smooth object. All right, so now let me try to make this a little bit more precise. So hopefully it will not be too technical. So I will be looking at schemes over an algebraic, over a field of characteristic 0, might as well assume it's C. That's where the most, you already see pretty much everything over C. And technically, I'm going to study categories over this scheme. So yeah, I put some adjectives here to make it precise. So I want the categories to be incomplete differential graded categories. And so technically, I guess this is the definition, that when I talk about categories over B, I'm thinking about categories that are acted upon by the tensor category of quasi-coherent sheaves on B. So in other words, these are modules over the category of quasi-coherent sheaves on B. So now I said quasi-coherent sheaves here just because it seems maybe more natural in this situation. However, the category of quasi-coherent sheaves is big. So it's good to know that in reality, you don't need to work with all quasi-coherent sheaves. It's enough to consider compact generators. So it's the category of quasi-coherent sheaves is always generated by perfect complexes. So by coherent, well, bounded coherent complexes of finite Tor dimension. So what this means is that in practice, in practice, the action of the entire category of quasi-coherent sheaves is determined by just action of the perfect complexes. And moreover, if I have some specific generators, it's enough to know how the generators act. For example, if B is affine, this entire category is just generated by one object. And because of this fancy notion of categories over B reduces to something more familiar. It's just categories that are linear over the coordinate ring of the affine scheme. So in other words, I want all the spaces of homomorphisms to be modules over this ring.
Dima, excuse me, do you mean the abelian category of quasi-coherent sheaves or the DG category of complexes?
I mean the DG category. So, sorry, all categories, there will be no abelian categories in this talk. Okay. So everything is DG and derived. But the point is that we won't get to the point where this the specific techniques of the G categories will matter. Okay, and so yeah, so in reality these are just categories that are linear over. So if B is affine, these are just categories that are linear over the coordinate ring. And maybe a more general example is, so to say, the categories of geometric origin. So if you have another scheme to B, then the category of either quasi-coherent or perfect sheaves on B, whichever one, whether you prefer working with large category or small category is irrelevant. So this category will act upon the category of sheaves on Y, quasi-coherent sheaves on Y, using pullback. So if you want to act by an object downstairs, you can pull it back and tensorify it. All right, so I already said that, I mean, it would be kind of nice if I could just consider affine schemes all the time, and then everything would maybe would be easier to understand. Unfortunately, but the story becomes interesting when I start talking about proper morphisms, and there are very few proper morphisms between affine schemes. For this reason, you might also want to keep in mind this observation that even if B is, for example, quasi-projective rather than affine, we still know we still understand we can still understand the action, the structure of a category over B, because in this case, it suffices to understand what happens when you act by vector bundles. And so this is one way to make this notion maybe more concrete. And the other way, again, just like usual in algebraic geometry, you can try to understand things by embedding them into projective space, or you can try understanding things by covering them with affine charts. And so the claim is that you can also understand categories of B over B by taking this notion of a linear category and then globalizing it by patching various affine charts in B. So for example, if I have P1 covered by two A1s, then what I'm interested in would be a category that's linear over one polynomial ring, another category that's linear over another polynomial ring, such that when I pass to the double intersection, the two categories are, I have an equivalence between localizations of these two categories. So in reality, there is a theorem hidden here. So the theorem is that this notion of categories over a scheme can be glued by looking at affine charts. So this is this is known as one affinity, and so this notion was introduced and studied by Dennis Gatesgory. So he has a paper specifically on this subject where he shows what things are one-affine and which things are not one-affine. And well, the point is that schemes, fortunately, are one-affine. By the way, the reason, I mean, maybe I should, I was just going to say that if you look at this notion, of category over B, you will see that it's a little bit similar to saying that, say, quasi-coherent sheaves on B are just modules over some algebra, over the algebra of coherent sheaves, over the algebra of regular functions on B. This definition, if I work with quasi-coherent sheaves, this definition is correct, but only if B is affine. And somehow the point of this terminology, the point of this definition is that somehow when you deal with categories, all schemes behave as if they were affine. So they are all one affine. Okay. So now we come to the main point. I don't know this is probably the scariest slide in this talk. So let's see if we can get through it. So the claim is that this notion of categories over a space admits a particular kind of descent. So in this case, I will be talking about proper descent, and this is very close. It's almost like Hitchhiker's Guide to the Galaxy. It's like almost quite entirely unlike something written in those papers, but no, in fact, it's very close to what's written in those papers. But I cannot, for example, I cannot pinpoint the precise place where the statement is given in these terms. So let me give the statement then. So the point is that this kind of categories, in many ways, they are an upgrade of quasi-coherent sheaves. So this is maybe the slogan. And being upgrades of quasi-coherent sheaves, they can be pulled back. So given a category acted upon by B, given a category over B, I can tensor it. So if I have X mapping to B, I can, so to say, change base. I can take this category and tensor it with the category with this bigger monoidal category, and get a category over X. And the key point is that this new category will actually, so the point is, the question of descent, as usual, is to what extent I can reconstruct the category I started with from this base change, from this extended category. And this requires descent data. And it turns out that in this case, the descent data can be understood as the action of quasi-coherent sheaves on the fiber product of X and B. So let me see if this becomes any more reasonable from this example. So let me suppose, maybe I should have written this. So let me suppose that the category C is just quasi-coherent sheaves on Y viewed as a module over quasi-coherent sheaves on B. So quasi-coherent sheaves. So it's a bilinear category. It's a bilinear category. Now, when I consider it as a, when I do this operation, when I pass from C to C prime, this has the effect of looking at this, at the fiber product. So instead of looking at sheaves on Y, I am now looking at sheaves on X cross Y over B, on the fiber product of X and Y. And the question, and now my question is, okay, so suppose I know sheaves on X cross Y over B, how do I recover sheaves on Y? And the claim is that you can try doing this by using descent. And the way you would do this is you would, so the descent data would amount to the action, geometrically, the descent data comes from the action of this groupoid on this scheme. And in terms of, this leads to the action of the quasi-coherent sheaves on this groupoid on the category C prime. And this action, if I write it out explicitly, this action will be given by a convolution formula with respect to various projections. So somehow the descent data for this in this picture comes from the action of this monoidal category on C prime. All right, maybe. Did it make at least some sense? I realize that this is maybe too much to take in if you haven't seen these things before, but is at least, if there are any questions, maybe it's better to ask them now rather than wait.
No, I mean, if you know the diagrams for the usual descent, you can. And the second remark is that there is a kind of a non-commutative version of that. There is a paper of Maxim called Geometry of DG Categories, where, I mean, he works with affine setting, like associative algebras, but in the end, everything is formulated in terms of the analog of your category A. It's some kind of co-algebra. Yeah.
Yay. So yeah, so this is pretty formal. Yes.
Can you explain the use of the groupoid on X?
Right. So yeah. So the point is that this is just general. Let me add it. This is just general. Point is that whenever I have, in any situation where I have a map from X to B, I can consider X cross X over B. And this is this fiber product will have a groupoid structure. Basically, so I can think of, so I guess more traditionally, I would say that I'm thinking of X as objects and X cross X over B as arrows going from one point in X to another point in X, provided they map to the same point in B. And then the point is that composition will make sense.
Okay, thank you.
Dima, and my question is again maybe too technical, so feel free to deflect it if it is. So what happens? So what I'm concerned about in this picture is that this category of complex of quasi-coherent sheaves is not an enhancement of the derived category. What happens if you take, say, category of injective sheaves with quasi-coherent homology?
So, I'll have to think about it. I cannot answer this immediately, but somehow the point is that this here, the reason things work out well is because I only only work with this DG co-complete category. So if you want, you can take this, you can strike out this category of quasi-coherent sheaves and replace it by perfect complexes. So, and this ability of going between perfect, so I'm kind of, I can only see categories that are compactly, kind of incompletion of compactly generated of small categories.
Yeah, yeah, I see, thanks.
Okay.
So Dima, what was the assumption on the map P besides properness?
Right, that's, that, I guess that's my signal to move on. So yeah, so as stated, there are no assumptions, it's just a proper map. But the point is that descent, if you actually want descent to recover information over B completely, you need this map to be a cover. So if this map is surjective, then the claim is that the original category C will be completely recoverable from C prime equipped with an action of this algebra. In general, something weaker is you can still make a precise statement, but it's going to be a weaker statement that this category, this A module only sees the part of the original category that's supported over the image of X. So inside B, so there is B. Inside B, there is the image of X, which is a closed subscheme. And so I have a category that, generally speaking, lives over the entirety of B, but the moment I restrict it to X, I'm definitely going to lose any information about what happens away from this image. And the theorem is that I don't lose anything else. In other words, this category, this module completely recovers the restriction of the original category to the restriction of the original category to the formal completion of the image. Does it make sense?
Mm-hmm. Thanks.
All right. So, okay, so here's the, and now we come to the crucial point. Now, in general, there's more than one type of interesting sheaves associated to a scheme. And well, because I kind of put myself in the corner, I'm only working with these categories that are generated by compact objects. For me, the crucial difference is between coherent sheaves, well, between perfect complexes and just coherent complexes. In other words, the crucial difference is whether things have finite Tor dimension or they don't have finite Tor dimension. And yeah, I stated it. So for this talk, I generally can work with small categories the whole time. So I can think, I don't have to int complete, although it's philosophically it might be better. So philosophically, I can look at int completion of coherent sheaves and int completion of perfect sheaves, which, well, this is of course just quasi-coherent sheaves and what. And so yeah, so this distinction is, for example, important in not in the categorical proper descent, but in the usual proper in the proper descent for sheaves rather than for categories. That's one place where it's really important to work with coh rather than int coh. Now, the good news is that I assume that X and B are smooth. And on smooth schemes, anything that has anything coherent has a finite resolution, please. So that means that on X and on B, this difference doesn't come into play. However, there was another object, this fiber product, where the difference becomes important. Even if X and B are smooth, this fiber product need not be smooth because the map is not smooth. And so what this means is that when I talk about quasi-coh X, quasi-coh B, you'd like don't need to pay too much attention about the to the precise category because I have only one choice reason. But here it's really important that I write quasi-coh, which is the, or if you like, that I work with perfect complexes rather than with coherent objects. So somehow a short point is that this fiber product, X cross X over B, generally speaking, is not smooth. It's only a complete intersection, or in the DG world, I would say that it's quasi-smooth, just different term for the same thing, but not smooth. So on this fiber product, I have options. And that's really where things start to get interesting. So let me try to draw some kind of a cartoon here. So I started by looking at categories over my smooth base B. And these were the same as modules over a particular tensor category. Well, if I'm writing perf, I might as well write perf here. I don't know. It's somehow more consistent to put perf of B instead of coh of B. So, however, now I have a map from X to B. So there's a map from X to B. And this map, generally speaking, is not surjective. So there's X, there is some closed subset in B. So I'm drawing it like it's a segment. In reality, I mean, it's an algebraic closed subset. So there is some closed subset in B, and so within this totality, within the two category technically of all categories over B, I can consider the categories that only sit over this P of X. In other words, they vanish if I restrict them to the open complement of this closed subset. So I have these categories, and the theorem, the proper categorical descent, tells me that these categories are the same as modules over a particular monoidal category, the monoidal category of monoidal category of modules of perfect complexes on X cross on the fiber product. So besides this X, there's also, I don't know, I probably shouldn't try to draw the fiber product of X over B, but it comes into play here. So, however, you have this monoidal category of X cross X over B modules, but there is a larger category of coherent X cross X over B modules. And so it turns out that the relation between these vertical categories, so between these two categories, the relation between categories acted upon by perfect complexes and those acted upon by coherent complexes, is completely analogous to the relation between these between all categories over B and categories over B supported by some smaller set. So somehow within, I mean, for example, this, I guess maybe let me make this precise. So what really happens is that on the one hand, these objects form a subclass. So what I have is, technically I should be saying that I have a full two subcategory. So of categories over B satisfying a particular property. But I also have some kind of adjoint functor, a colocalization construction, which takes a category over B and restricts it to the formal completion closed subset. And the relation is the same on the right-hand side. So anyway, so we have all that, but now the big problem, maybe I should add a few question marks, because that's the big problem. The big problem is to understand what happens geometrically. So geometrically, I started with things, I understood, like when I was at the first step, when I was here, I understood that somehow my objects lived over B. Then I went, I took one more step by considering a special kind of categories over B, and that actually made things more restrictive. Now I have categories over B, but they are only allowed to live over some smaller closed subset. Fine. Now potentially smaller subset. But now I'm enlarging this class. I'm reinterpreting this as modules over some category, and then I realize that these modules are a special, this class of modules, module categories, maybe I should say, can be enlarged to something, to this, to something for which I have an algebraic description, but I don't understand the geometry, because this enlargement, it still lives on X. So if I'm thinking in terms of the original space B, I still cannot see anything that lives on this open set. So somehow I still live in the confines of this closed subset, but somehow I managed to enlarge this class. So it's almost like this, this notion is growing in some kind of orthogonal direction. So this is the, and I wanted to say that this, from my point of view, this is like the easiest way to see how the, well, how you have some kind of additional notion of support in this theory. All right, let me really quickly look at an example. So this is the simplest example where everything is affine and you can still see what's going on. So in fact, in this case, my base will be A1. Maybe I needed a picture. I don't know why I don't have a picture. So there's A1 and there's a single point mapping to A1. So both schemes are affine, that's good. And the map between, and the map is a closed embedding in particular proper. So I'm in a situation where the theory applies. So let's retrace this diagram in this situation. So I start by looking at categories over A1, and because it's affine, I'm really thinking about categories that are linear over the polynomial ring of functions on this A1. Now, within this category, I have within all of those categories, I can look at only the categories that are supported over this one point, and this corresponds to considering linear categories where T acts locally nilpotently. This is, again, just the basic idea that if you localize, so this is the condition that tells you that when you invert T, when you localize to the open complement of the image of X, you're going to get 0. Now, their proper descent tells me that these categories are actually in equivalence, in one-to-one correspondence, so to say, with categories acted upon by quasi-coherent sheaves or perfect complexes, again, whichever one you prefer, on the fiber product. Now, well, this example is really simple. Unfortunately, one thing is that I cannot do it completely classically. It cannot be done completely classically because when you consider the fiber product of X with itself over B, because the map is not flat, it takes you outside of classical rings. So this is going to be a fine derived scheme, but a very simple one. So it's a DG algebra with one generator in homological degree 1. So just zero-dimensional, one-dimensional, zeroth homology, one-dimensional first homology, and nothing else. And the point is that besides these categories acted upon by, so besides looking at perfect complexes, I can also look at coherent complexes, and that allows me to enlarge the notion of modules over this monoidal category. So again, this algebra doesn't have finite global homological dimensions, so there are interesting objects. There are interesting coherent non-perfect complexes. Now, notice that here I said categories acted upon by, should be acted upon by perf, instead of saying linear categories. And I cannot do this. These are not just the categories that are linear over this DG algebra. And that's due to one subtle point. Maybe it's easiest to demonstrate, well, either in this example or in this picture. The point is that I was, the point is in this line, that somehow when I talk about action, when I talk about the monoidal structure on this algebra, the monoidal structure doesn't come from plain tensor product, rather it comes from convolution. So, however, in this particular example, we can simplify things by using Cazul transform, which behaves a little bit like the Fourier transform. So it takes convolution and turns it into a tensor product. So, and in this particular case, it turns out that these two classes, the categories acted upon by perfect complexes and categories acted upon by coherent complexes, will become very similar to this vertical line is actually very similar to the horizontal line, because the Cazul transform, the Cazul dual of this ring, is also a polynomial ring. The only difference is that it's graded differently. So it's a polynomial ring with a gradient where the degree of the generator is 2. But other than that, it turns out that you get the same picture. So you get, you can have categories that are linear over this graded ring, and within those you have categories supported over a point. So let me maybe, again, I don't know, hopefully this made at least some sense, but let me try to summarize what's going on here. So, because that's could be a crucial point. So we start by studying categories over A1. So this linear so you have this A1, and on the other hand, let's try to do it the way they dig tunnels, right? So let's move from opposite directions towards the middle. So the category, on the other hand, I have a category that is linear over a graded version of A1. So I have some, I shouldn't really draw it as A1, but I'm going anyways. So this is A1 graded. So this is C of eta has degree 2. Now, by themselves, these are just two different classes of categories. I can work with categories linear over the polynomial ring. I can work with categories linear over a graded polynomial ring. Fine. But it turns out that if on both sides I impose some restrictions, namely I constrain the support, I demand that the support should be just one point. So on the one side, I would say that the coordinate on this A1 must act nilpotently. On the other side, I will say that this graded eta must act nilpotently. It turns out that once I do this, the corresponding classes of categories are identified. But they are identified in a completely non-trivial way, because this identification included, it's not something that, well, I mean, you can write it explicitly, but it's not something tautological, because on the one hand, I have this equality sign includes proper descent, and this passage includes Kazul transform between these two rings. But however it happens, what we can do is we can somehow, so somehow you have this totality of interesting categories growing over one A1, totality of interesting categories growing over the other A1, but what happens over marked points is actually the same. So you should be able to patch these things together to get to something that lives over a cross. And this cross is kind of an explanation of how, well, so it's like I said earlier that somehow the geometry is supposed to grow in orthogonal direction, and this A1 is the geometry that grows in the orthogonal direction. All right. So let me now try to summarize. Let me peek ahead. Yeah. So now I can finally formulate the statement, and this will be the answer to the original question, like what is the geometry underlying this situation? And this is so. I want to formulate the theorem precisely, which means that, well, because I cannot go into details, I will make the statement slightly weaker than, it will be very precise, but slightly weaker than one would want to, then I could do it. And then I'll try to explain what actually, somehow the big picture, but less precisely. So the precise statement is that when I work, so let me consider this situation I was looking at before. So I have X mapping to B, the map is smooth. Sorry, no, the map is not smooth. X and B are smooth, the map is proper. So if in this situation I work with perfect complexes on X cross X times B, then I'm not going to see anything interesting. This will not take me outside of B by proper descent. So let me do the more interesting thing, and let me consider all coherent complexes on X cross X over B. And so this has a monoidal structure, technically given by convolution. And I can consider modules over this category. Technically, I'm studying this as a two category. So I'm studying the two category of all categories acted upon by this object, by this category. All right, and so the claim is that this two category, in fact, doesn't depend on X, but only depends on some geometry in the cotangent bundle of B. Namely, when you have a proper map from X to B, to this situation, you can associate a conical as an isotropic subset in the cotangent bundle to B, which I'm going to denote it as the conormal bundle to X. It would literally be the conormal bundle when the map is a closed embedding, like in this example. So the meaning of this line is that it's the conormal bundle to 0. And yeah, here's the definition. It's, so to say, things, the conormal vectors to B that are annihilated by some, by the codifferential at one point in the preimage. Right, and so, yeah, so that's what the theorem says, that in fact, you can consider all many different x's sitting over B, but somehow so it's like, you can say that what I did before was some kind of enlargement of the notion of enlargement or extension in a non-trivial direction of the notion of category over B. However, this construction required taking a specific x, and now I want to control over the totality of various spaces x. So I want to know how many different enlargements there are, and the claim is that, in fact, x itself doesn't matter. What matters is this conical isotropic subset. So, by the way, just like in the one categorical level down, you can view this as a kind of Morita equivalence statement. So when I say that the category of modules over something depends only on some data, this is equivalent to saying that if I have two such spaces x corresponding to the same conical isotropic, then the corresponding monoidal categories are Morita equivalent. All right, so this is, as promised, this is a precise statement, finally. But now, what actually follows from this? Now, the things become interesting. So, well, this is a picture, kind of trying to explain what I just, so it's basically, it's the same kind of picture, but now with geometry added to it. So I have the cotangent bundle to B. I can consider all categories over B, which from this point of view correspond to the 0 section of the cotangent bundle. Then if I have a map from X to B, I have a subset within this 0 section, namely the image of X. And categories sitting over this image, well, I understand them as modules over some perfect complexes. However, I have this I have this larger object, this I can consider module categories acted upon by the monoidal category of coherent sheaves, and this somehow introduces objects correspond somehow microlocally, I guess, sitting over the normal cone. So I have some kind of conical isotropic subset sitting over the 0 section, and I know how to define objects, how to define categories sitting over this. Now, putting this all together for all various x that map properly to B, I will be actually, I will be able to deal with arbitrary, what am I saying, isotropic conical. So let's see. So for any conical isotropic subset in the cotangent bundle to B, we will have some objects that are natural to call categories sitting over this, or microlocally supported over this over this locus, over this conical isotropic. And it's, in reality, it's an extension of the usual notion of categories over B. So categories over B correspond to the special case when this conical isotropic is just the zero section. And so the point is that if you actually want to describe these objects explicitly, you have to take your conical isotropic and come up with some X. So you need to, so the description, an explicit description will depend on a choice of some extra data, but then there is a fact that claims that various choices of X don't well, lead to the same answer, lead to the same, even though the corresponding monoidal categories might not be equivalent, they are Morita equivalent, so modules over these monoidal categories are the same. All right, so this is all I wanted to say. I hope that it made at least some sense, and well, thank you anyways.
Yeah, thank you, Dima. Other questions?
Do you have an idea as to the singular support claim you will need on locsys, like for the local geometric Langlands?
The idea as in terms of formulation or in terms of proof. So formulation is very similar to the global geometric Langlands claim. So the claim is that there is, so in the, where is it say? Yeah, so in the global geometric Langlands claim, the point was this, well, the point is in this word prescribed, that there was a specific conical subset in the shifted cotangent bundle to local systems corresponding to nilpotence, basically to nilpotence of a Higgs field. And geometry is actually very much the same in the local settings. So it turns out that this stack is smooth. Its cotangent bundle, the cotangent vector corresponds to basically having a Higgs field in addition to the bundle with connection. And you can, if you require this Higgs field to be nilpotent, so this will provide a specific local, this will provide a specific conical Lagrangian subset.
Thank you.
Right. So, and
no, go ahead.
Yeah, I wanted to say that in fact, there is one situation where this appeared in some form, and this is Bezrukamnikov's work on the affine Hecke algebra. So in the affine Hecke algebra, so in his description of the affine Hecke algebra, they appear something very similar to this, well, to coherent sheaves on the fiber, on certain fiber product. And from this point, so this theory explains why, so this fiber product is a little bit weird from the point of view of classical Langlands program. So roughly speaking, we start by looking at G, that's fine, but then for some reason Borel group or Borel algebra appears. And from this point of view, this explains the mechanism of this appearance. That's what's important is not, because X is not important. It's this cotangent, it's this subset in the cotangent space that is important. So from this point of view, this his description, it's like, yeah, his uses a specific space to describe this particular two category in one situation.
So what's the support in his story?
I mean, it's always nilpotent support. So the point is that you have G he's dealing with well, it's Lie algebra, or it's the group, or it's the moduli stack of local systems on the punctured disk. Let's not worry about this, especially since he works in the neighborhood of zero anyways. But the point is that the cotangent bundle in this case corresponds to having two elements in the, let's say, in the Lie algebra. In reality, everything is supposed to be G equivariant. So when you do when you consider cotangent bundle, the two elements must commute by the moment map condition, but that's not important. Anyway, the support corresponds to the condition that one of these elements must be nilpotent. So that you have one, the one that sits in the cotangent bundle.
Okay. Also,
sorry,
there is.
I didn't hear the details of the comment, but it sounded right.
It's another resolution. Sorry.
Yes. Yes.
Also, there is a question in the chat from you, Feng. It's a question where the results about quasi-Koch automatically true for int Koch.
Which results?
Whatever, I don't know. Actually, there were no results. There was a construction, but there was also a theorem.
Yes, but I mean, in some sense, the whole point is jumping between quasi-Koch and int Koch. So I'm not.
Okay, so.
Yeah, I mean, I need more details about the question. Yeah.
Okay, I also have a question. Are there any applications beyond the, I would say, beyond the algebraic geometry?
Well, this is on the nose of it. It could be, but yeah, on the nose of it, this is algebraic geometry. So
no, this I noticed, but
no, but I mean, there is this, from the point of view of, if you just look at algebra, from this point of view, what goes on is a little bit like this. So you start, I mean, let me just go maybe one or even two categorical levels down and talk about what's going on. It's like you have you're studying some, you're studying something, maybe some category. Then there is an object, and you realize that you can understand, if you look at endomorphisms of this object, then this algebra will tell you at least, it will give you partial information about the category, or more precisely, you will only see the part of the category that's generated by this object. However, what happens here is that the algebra of endomorphisms admits an enlargement. So somehow, so you can, so it feels to me that whenever it's like, how should I say it? You can also argue that what's going on is an interplay between large and small categories, and this is maybe closer to the work of Hermann Stefanic. But I'm not. He had these ideas, but I'm not sure. There was some question, and I don't know if this question has been resolved. But anyway, so let me just say it, and you should feel free to ignore it if it's not helpful. So you can say, okay, let's, in the situation where X maps to B, I can consider, so just for purely algebraic reasons, this category, so there's a purely algebraic reason for working with this category of quasi-coherent sheaves on X cross X over B, and that is because this is the category of endomorphisms of the category of quasi-coherent sheaves on X over the category of quasi-coherent sheaves on B. Now, what happens is that this category of these categories are compactly generated. So to say that if I have an endomorphism from quasi-coherent sheaves, this endomorphism is uniquely determined by where it sends perfect complexes. But so this is just the same. This endomorphisms for quasi-coherent sheaves, this is the same as homomorphisms of a perf B from perf X to quasi-coh of X. But suppose that you don't want that. Suppose that you want to deal with smaller categories. So then there are two natural ways to introduce the notion of smallness. One, so it's basically there are two orders. You can take maps and then take compact objects in maps, or you can take maps between compact objects. So there are two different orders and they lead to different results. Namely, within this category of quasi-coherent sheaves on X cross X over B, I have its own category of perfect objects. It has its own notion of smallness, which are these perfect complexes on X cross X over B. Alternatively, you can reinterpret this category as follows, and then ask, okay, well, among all those morphisms from perf X to quasi-coh of X, which ones actually land in the small category here? So this is closer to actually Benzvi, Nadler, and Pragel's work. So in other words, what is this home? It's by construction, it's a full subcategory in this larger category. So in other words, I'm asking the following question. What condition should a sheaf on X cross X on this fiber product satisfy so that if I convolve it with something perfect on X, the result is going to be perfect. The output will be perfect as well. And the answer is that this condition is equivalent to coherence. And because X is not, because X was smooth, but the fiber product is not, these two things are different. So these two things are different, and that's basically the origin of this enlargement.
It's
but
like
now,
go ahead.
I wanted to say that now this construction was in some sense very formal. I said, okay, let's suppose I have a compactly generated category, and that's acted upon by another compactly generated category. Then I can do two different things. I can take the category of homes and look at compact objects there, or restrict immediately to compact objects and consider only homomorphisms that send compact to compact. So it seems like something algebraic, but
no, not necessarily. It's like integral operators with a
Yeah,
kernel which has compact
Absolutely.
support in each variable.
Yeah, absolutely. So yeah, so when I say algebraic, I mean that it's I'm using it as an I guess in opposition to algebra geometric, that there was no almost no geometry here. Yeah.
Also, I have a question. What is three-dimensional in the story? Since you mentioned Kapustin, Rozansky, and Saulina, if I remember correctly, it was something about three-dimensional theories.
I'm probably the wrong person to ask this. So from my point of view, I can say that so what is closer, how I can relate what I was talking about to what they're saying. So they were talking about certain matrix factorizations, and these matrix factorizations, well, especially in the version where you look at graded matrix factorizations, this is a precise way to, well, not a, this is a way to, well, a way to describe explicitly, in some sense, this category of coherent sheaves. And there, an important point in their construction was an introduction of extra parameters. And this extra parameter, so it was like looking at matrix factorizations with extra parameters. And these extra parameters exactly correspond, well, these extra parameters correspond, maybe I shouldn't use the word exactly, but they correspond to looking at covers. So looking at X, that is, so these extra parameters should be thought of as coordinates on X that's mapping to B. Now, this is as much as I remember right now. I must admit I haven't looked. So this is mostly, this is a reaction to a talk by Rosansky. So I
also remember in this algebra with generator Xi, which people wrongly call Kapustin algebra, physicists, of course.
Okay.
Yeah, that's true. Okay, now I see in the chat that you, Frank, clarified. Yeah, go ahead. Just ask yourself.
Okay, so let me reformulate my question. So I was lost for a while during talk. So are you realizing nilpotent support of indical by singular support of conical?
No, this is, it's an upgrade, if you like, of int core and quasi-core. So I'm dealing, so I'm studying categories. So these are going to be categories of modules over something. And it turns out that in the relevant situation, the category of, the important geometric object, this X cross X over B, turns out to be only quasi-smooth. And for this reason, the distinction between quasi-core and int-core on this object comes into play. So if you like, you can say that I'm in a way, I'm bootstrapping the theory to the next categorical level by saying, now, if I'm studying categories over something smooth, I study them by means of descent, and that involves mapping things to B and then taking the fiber product. But then this guy was, B and X were smooth, but the fiber product is only quasi-smooth. So on this fiber product, I have a theory of singular support for coherent sheaves. And this gives me, this theory of coherent sheaves somehow give this theory of singular support, this various different categories that I get for singular support, give me the notion of singular support for categories on B. So somehow the cotangent bundle on B, or more precisely, the cotangent bundle on B and the map from the cotangent bundle and the differential of this map appears as the shifted cotangent bundle on this quasi-smooth guy. I don't know, did it make sense? I'm not sure.
For me, it does.
And one more question.
Yeah.
Could you please clarify again how this notation of singular support is connected to categorical one affinities?
This is before the singular support appears, really. So the way this well, it's possible that I'm using this one affineness of all. Yeah, I don't know why I said affinity. One affineness of all of schemes more than once. But my point is that I gave this definition, right? Of so basically in the entire talk, I was looking at modules of various monoidal categories. And I find this very very natural, maybe very algebraic approach. But if somebody, this is not necessarily the first definition of category over an object that you would, well, you would come up with. So if just like when you define coherent sheaves over a scheme, you can define them by looking at modules over affine charts and then gluing conditions. I could define categories over any categories of a scheme by looking at categories that are linear over various rings of functions over various patches, and then gluing those together. So I don't know if it will help to look at things more concretely. Like I can say, okay, on P1, I can consider categories that are that are linear over C adjoint Z. Then I can consider collections consisting of a C of Z linear category, C of Z inverse linear category, and an equivalence between two localizations of this category. If I localize the first with respect to Z inverse and the second with respect to Z, the two things are supposed to be equivalent. So I could define P1 categories over P1 like that. And the claim is that this is equivalent to defining them as categories acted upon by perf of P1 or by quasi-coh of P1, doesn't matter. And this is exactly their fineness.
Thank you very much.
Okay. Any more questions? Well, if not, then I'll thank you, Dima, for very interesting talk. Thank you.
Oh, thank you for the invitation.